Okay, let's talk about 0, 1 binary tree. Here is a problem. We are given this kind of a tree. It's a binary tree, but the only value allowed is 0 and 1. And for any node, the left branch is the same as the parent node, and the right children is different than the parent node. Take this node for example. The left node is the same as the parent. The right node is different than the parent. And we are given two numbers. The first number is a level. The second number is a position within that level. 3, 2, we go to level 3, position 2, and 1 is the value we want to return. And 2, 1, we go to level 2, position 1, and we want to return 0. If we are given 3 and 3, we want to go to level 3, position 3, and then we return 1. So given a random number level and the position inside that level, how can we calculate the value? First approach we will try is we do a level traversal of the binary search tree. When we traversal, we will count how many nodes we just passed. And until the count equal to the total number of nodes we have to travel, we know we just reached the target position, and we can print out the value. So in order to do that, we first need to travel to the level. In order to travel to the target level, the node we have to pass is equal to 2 power n minus 1 minus 1. So in this case, n equals 3, and 2 power 2 equals 4. 4 minus 1 equals 3, so we need to travel 1, 2, 3 node before we reach level 3. Then what we have to travel is the rest of the k elements before we reach the target position. Knowing that the code is natural, and the level traversal of the binary search tree is standard. We offer the root node. Let's ignore those two lines at this moment. We offer the root node to the queue, and as long as the queue is not empty, we get the top node from the queue, and we offer the two children of that node. If for left branch, the value is same as the parent, for the right branch, the value is different than the parent. Then we just add the two children nodes into the queue. We keep adding those. And when should we stop and return the value is decided by the counter. Each time we each time we visited a node, we increase the counter. When the counter reaches our target, we return the current value we just visited, and the limit is calculated with this formula we just introduced before. And this approach, we need to increase counter this amount before we can return the value. And the k in the worst scenario could be the loss levels element number, which is 2 power n minus 1. So our total time complexity for this is 2 power n, and the space cost is bounded by the queue size, which in the worst scenario is equal to the number of elements in the lost level, so which is 2 power n minus 1. This approach can give us the correct answer, but we can have a better, faster approach if we can use a bottom-up recursive. Okay, imagine we already positioned as the target position. We at level 3 and 2, and then we can trace back to figure out do we in the left branch or we are in the right branch. So if we walk back, if we trace back the parent node, we either end up here or end up here. That will decide which side we are. Then once we know this is 0 or 1, we can walk down to the binary search tree until we reach the level n and we return the value. So this is how the code works. We first find the parent. The parent node we know for sure is at level n-1, and the parent position is at k plus 1 over 2. So how that works, if we are at position 2, 2 plus 1 equals 3, 3 over 2. Integer division equal 1. So for position 2 here, the parent node end up at position 1. The same thing here, if we have node 4, right? Position 4, 4 plus 1 equals 5, 5 over 2 equals 2. So we end up here instead of here. This is how we walk up the binary search tree with this calculation. Level -1, position k plus 1 over 2. Once we reach the top level, we can figure out we are on the left branch or the right branch, and we either return 0 or 1. Once we have that information, we can pop out from this recursive call. We get the parent. Depending on if we are level is on the left branch, we return parent. If the position is on the right branch, we return a value different than the parent. And when we walk down to the level n, and whatever we return is the final answer. So let's look at the code. Imagine we don't have that yet. So we first call this final node with value 3, 2. We execute this line, n equals 3, so we will not return. We run this line, and the parameter we're passing will be n-1 equal 2, and k plus 1 over 2 will be 2 plus 1 over 2, which is 1. So we recursively call this function. So then we go here. N equal 1 is not true because in this case our level equal 2. And so we go the next line, and the parameter we're passing is n-1. 2 minus 1 is 1. And k plus 1 over 2 is 1 plus 1 over 2 is 1. So this is a parameter. So recursively call this. And so let's run this line. N equal 1, which is true. So we need to return k minus 1. K minus 1 in this case, 1 minus 1 is 0. This is what we return. So we return parent equals 0. And we check k mode 2 in this case. K is 1. 1 mode 2 not equal 0, so we return parent. Parent is 0, and we return 0. And so we pop out from here, and we are in this method. And parent is 0, and let's check k mode 2. In this case, k is equal to 2. 2 mode 2 equals 0, so we should run this line. In this case, parent is 0. We need to return a different value, which is 1. So if we are given 3, 2, we should return 1. And here we use two different approaches to calculate the same level and position. And for 3 and 2, they both print out 1. And to double check, we increase the level from 0 to 1 at each level. We iterate through all the possible positions, and we compare the two methods, see if they have the exactly same value. If they are exactly same, we just print out perfect. So let's run the program. Perfect. And this approach, recursive approach, have time complexity on because we have to go up from the level n to level 1 in order to return. And the stack depth is n. Once we return, we need to pop from this recursive call, and the stack depth is n, so the time complexity is O(n). At each stack call, we only have a limited number of variables, so the space complexity is also O(n). That's 0-1 binary tree.